So let's move on to our next question. I think this one is probably going to be functionally a little bit more useful to us, especially thinking about the ways in which gases could come up in future topics. What we're looking at here is using, again, PV equals nRT, but in, I guess, a more useful way in the fact that we have a gas, we have the measurements of all of the variables except for one, and finding that unknown variable to then be able to do some other kind of calculation with that unknown value. In this question, it says, what volume is needed to store 0.62 moles of gas at a pressure of 3.6 times 10 to the 5 pascals at a temperature of 295 degrees Celsius? So what we're trying to find is V, what volume? So V is unknown. And we have been given the number of moles, which is 0.62. We've been given the pressure, which is 3.6 times 10 to the 5 PA, or pascals. And we've also been given the temperature, which is 295 degrees Celsius, which we should be converting immediately anyway, because we are working in Kelvin always for these calculations. So 295 plus 273.15 will give us the temperature in Kelvin, which is 568.15. And the other part of our equation is R, which is the gas constant. Now, gas constant, its value is 8.314. Now, it's written in your data sheet as joules per mole per Kelvin, but that isn't particularly helpful to us because we're working with pressures and volumes. I'm going to be doing mine as 8.314 cubic meters times pascals per Kelvin per mole. All right, so what that means is the volume that we get at the end is going to be measured in cubic meters. The pressure is measured in pascals, and the temperature is measured in Kelvin, and as always, N is measured in moles. So using this data, what we should be able to do is rearrange our equation to calculate for V. So I'm going to be doing that over on the side here. So V is equal to nRT divided by P. And all that we need to do at this point is substitute and calculate. So N is 0.62, R is 8.314, and T in this equation is going to be 568.15 Kelvin, all divided by our pressure, which is 3.6 times 10 to the 5. So putting that into our calculator. So I've got 0.62 times 8.314 times 568.15, all divided by 3.6 times 10 to the 5. And the value that we get at the end is 0.008135, and that's going to be measured in cubic meters. So let's get that written down now. Remembering too that we need to make sure that we're using an appropriate number of significant figures. Both of these two values here, N and P, only have two significant figures, so that's what we should be reporting to. I'm also going to be writing in scientific notation. So that's going to be 8.1 times 10 to the negative. And so that's going to be negative 1, 2, 3 cubic meters. So that concludes Module 2, Introduction to Quantitative Chemistry. I hope that you've started to pick up on a lot of the quantitative concepts that, again, will underpin the rest of all of the modules for this course. If you don't feel like you fully understand every single concept in complete detail, don't fret. for a lot of these things, it's not the last time that we're going to be looking at a lot of these concepts. And for the most part, if we look at them again, they are going to be the important bits, but it's also going to mean that you're going to have time to practice some of these concepts in context when we start to tackle other parts of some of the other modules as well. Now, we're going to be moving into a depth study over the next few weeks, and it will be a while until you start to look at some of these videos again as we move into Module 3. But until then, have a good one.